to the seminar. It's my pleasure to introduce Sanaz Pooya, who will talk about K-theory of higher Kazhdan projections and applications to delocalized L²-Betti numbers.
Thanks, Karen, for the invitation. And I think I should apologize for not being quite the speaker, while my last name is not Pooya, but I'm quite close to it. So I think it's gonna be okay. No, this is okay. But in the announcement, it was written with. No worries, that's completely fine. So no worries, that's just right. Right. So today I'm going to describe or introduce a new construction of producing K-theory elements and study simply different trace pairing. So I will consider the canonical trace. We will see how the pairing between this trace and the new K-theory elements will be, and then I will introduce another traces, and then we will see how those evaluation will rise new invariants of groups. Right. So before getting there, so let's just see some already existing constructions. Yeah. I mean the mouse. Right. Right. Okay. So one very first one is when one has a finite subgroup, finite group, then one look at the averaging projection, which is just taking the sum over elements of the group G. That here we have UG. These are elements inside the C-star algebra. So we have just the averaging over the order of the finite group, and this gives us a projection. So the other one is Bott projection. So Bott projection is just when we consider a product of two commuting unitary and its generalization, then this would give us a well-defined K-theory or projections. And then the other one is when we look at the index of abstract Fredholm operators through the Baum-Cohn assembly map. So we have an abstract Fredholm operator. We look at the image under the Baum-Cohn assembly map, which is the index of that operator, and that is a projection. And one can study the K-theory class of this element. So these are like very well-known constructions. And the one that now I'm going to introduce, its motivation comes from groups with property T. So let me first tell you what property T and these projections are, and then we can later talk about this generalization. So take a group, a projection inside the maximal group C-star algebra or the universal group C-star algebra of G is a Kazhdan projection if it is of the following kind. So you are given a unitary representation of G. So one can extend this unitary representation from the level of group to a level of C-star algebra. So we get representation from C-star max of G to the unitary representation to the bounded operators on H being the given unitary representation of G. And now, if we look at this projection, so P is a projection. If we look at this, the image of projection inside bounded operators on H, this is the one whose image is described by the orthogonal projection onto the fixed vectors. So such a projection is called Kazhdan projection. So it's a projection inside C-star max, whose image as a bounded operator is the one to the fixed point by the group action. So some facts about this. So first, by the way we define this projection, this is unique. And it is non-zero. The non-zeroness is witnessed by the fact that the trivial representation has invariant vectors. So we can always see that through the trivial representation. Then if we are given an infinite group, so what is then this projection inside C star reduced? Well, we have an infinite group. Say a Kazhdan projection is the one whose image is the one onto the invariant vectors. But when we are considering the left regular representation, then the invariant vectors are the ones that are constant. So we are looking at constant functions, which are L2 at the same time. So these, because the group is infinite, then this constant, so there is only one, basically the zero function. So the image of this projection as an element of C star max inside C star reduced is zero, is the zero projection. And the existence of this projection is an obstruction to certain methods for proving the Baum-Cohn conjecture. So this is also quite well-known way or well-known method to find counterexamples. So now we say group G is so a group G has property T if such a projection exists in C star max. So one can define property T through various constructions, but the one that is interesting to operator algebra is the one where we require this Kazhdan projection exists. And now, so how does this generalization work? So if I'm going to generalize this definition of Kazhdan projection as being a projection whose image is defined by such a bounded operator, well, there is not enough material to generalize. So what should we generalize? So the first thing we would do is to kind of interpret this definition into something that allows for our generalization or for any generalization. So for that, I need to introduce the Laplace operator. So we start with the property T group. We know that property T groups are finitely generated. So there is a finite generating set, S, so coming through the definition, basically, or construction of property T. We fix our unitary representation, pi. Now we look at the Markov operator. So what is Markov operator? It's the one that averages over the generating set. Now, this operator has a very interesting property, namely its invariants are exactly the invariants of under the action. So one side is pretty easy to see if the operator, this Markov operator fixes an element, then obviously it is fixes. So one side is easy to see. If G is fixed by any generating element, and it fixes by the operator M. And to see the opposite, one just needs to use what is the use to convexity argument, exactly. To show the other way, one needs to use the convexity argument to see that invariants of pi and G and M are equal. So now one considered the Laplace operator, which is defined as the identity minus the Markov operator. So this is an element inside the group ring, but it comes with an interesting property, namely the kernel of Laplace operator is just the fixed point of the group action. Further, we can see that the fixed points are always defining the 0th degree cohomology with the coefficient in our given fixed Hilbert space. So the 0th degree cohomology corresponds to the kernel of this operator as now what we have here. And now having this, then when the 0th degree cohomology appears, then one can see how one can think of generalization, because one can think of higher degree cohomologies as a generalization of this notion. And that's what we're going to do. So I'm going to define higher Laplace operator, and through that define my generalized Kazhdan projection. So I said property T groups are finitely generated. So now if I'm going to introduce a higher generalization of that, then I need something that supports finite generation on the 0th degree, basically, being my property T. So for that, I assume my group G to be of type Fn+1. So that means that group G, my given group G, has a model for its classifying space Bg that is finite until degree n+1. So in other words, the free ZG module Z has a resolution that is until degree n+1 finitely generated. So given such a resolution, then I can apply my home functor to this, and then I get a CW complex, or in this case a complex of Hilbert spaces, because I can identify home BGN, so the n cells, with just a direct sum of as many Hilbert spaces as I have in that cell. And then now Laplace operator in degree 0 just be basically, in order to construct Laplace operator in degree 0, one just needs to look at this codifferential here. So it would be just D0 star D0, and it acts on this Hilbert space. While higher Laplace operator is defined basically, let's say, at degree n as an operator acting on this Hilbert space, and it involves this codifferential and this codifferential. So dn star dn plus dn minus 1, dn minus 1 star, basically the maps getting out and coming in. And here, we simply don't have anything before this, so that's why we end up with just one term here. So this is a combinatorial higher Laplace operator. And now there is a Kazhdan isomorphism which gives us an isomorphism between the nth degree reduced cohomology of G with coefficient in our Hilbert space, a given Hilbert space H, and the kernel of this higher Laplace operator. Just a recall, so what do we mean by reduced cohomology? This means that, so we have standard cohomology in degree n would be just the kernel divided by kernel of dn divided by the image of n minus 1. And in order to define the reduced cohomology, we just take the closure of the co-boundaries or the images in order to get a Hilbert space. Because if we don't do it, then we don't get a Hilbert space, and we need a Hilbert space. So we are working hence with reduced cohomology. And by Kazhdan, then we get this beautiful isomorphism here that identifies the kernel of delta n. So now what is the, what? I'm missing one slide here. Okay, so I should then give the definition here. So what are now our higher Kazhdan projections? So given a resolution as we saw associated with a group of type Fn+1, then En is a projection such that its image is the kernel of delta n and in contrast to Kazhdan projection, which was defined basically, that was projection from H to the invariant vector of H. Now here we are having our projection in degree n from some direct summon of this into basically the kernel of delta n being a subspace of this direct sum. So that's the difference. So here, this was just directly, so this is Kazhdan projection. Coming from property T. And the difference here is that instead of defining right away this projection as an element on the Hilbert space, we have it on a direct sum of Hilbert space. So as such, it lives in some direct sum of Hilbert spaces here. But it doesn't matter because we are interested in the K-theory element. And we have this Lagrangian K-theory to go to the matrices over our C-star algebra. So that will not cause any trouble for us. So that's just the difference that we see. So higher Kazhdan projection would be then the projection onto the kernel of this higher Laplacian. Right. So this is the first time that I am missing any slides, like basically the main slide of this part. Anyway, so the reason is that yesterday night I was just playing with my slides, and then as a result I forgot to add this one. Okay, so right. So now we have our Kazhdan projections, and I explained at the beginning that our aim is to study some trace pairings. So in order to do that, or in order to see what we get, so I am here recalling first one notion, and then we will see how this trace pairing will look like. So recall a group von Neumann algebra is just the weak star closure of the group ring inside bounded operator on L2 of G. Group von Neumann algebra comes equipped with a very special trace, the canonical trace, which takes a finite support function in CG or in L1 of G and picks the coefficient in front of the identity element. So that's what this canonical trace does. And now here is one thing to observe. So we have our module or our reduced cohomology, and this one, so this is a right module because we have the action of G on L2 of G, and that extends to the action of the group von Neumann algebra on this module. And as a right module, this is just projection times L2 of G, a direct sum of L2 of G's. And what is this projection? This is precisely our higher Kazhdan projection, because we said higher Kazhdan projection is basically the kernel of delta n, and by Kazhdan isomorphism, we had this isomorphic to the degree n reduced cohomology of G. So the projection that we get here is precisely our higher Kazhdan projection. So it arises very naturally in this construction. And now the von Neumann dimension of this module, by definition, is just the tensor product of the matricial trace with this canonical trace evaluated at this projection that we have here. And for us, it's just this higher Kazhdan projection. So the result of this evaluation is just what is defined, what defines the dimension, the von Neumann dimension of this module. And now the nth L²-Betti number of a group G is just this von Neumann dimension that we just described. And as such, it lies inside this interval. So it's a positive number. And if we require G to be finitely generated, then of course we don't get infinity, but it can define for any group, a discrete group. Right. So this is the notion of L²-Betti numbers. And now what do we see here? Well, here the trace pairing between this trace and projection, our higher Kazhdan projection, give us the L²-Betti number. But these are trace in part, so they satisfy tracial property. So this means that this trace would be constant on the Maury von Neumann class of Pn. So what this means is that for a discrete group G, if Pn belongs to some matrices over the C-star reduced of G, then the trace pairing between this trace generalized to the K-theory level would be the L²-Betti number, nth L²-Betti number of our group G. So that is, and in particular, this implies that if the nth L²-Betti number is non-zero, then this would mean that the K-theory class here is non-zero. So we get some criteria for not having this K-theory class vanish inside K0 of C-star reduced G. Right. And now there is a conjecture by Luke saying or describing the image of this trace induced on the K-theory level or generalized to the K-theory level. And the conjecture is that such trace pairing lives inside the subring of Q generated by the inverse of the order of finite subgroups of G. So what does this say for the values of Kazhdan projection? It says that if we assume a G discrete and we assume that Pn lives inside matrices over C-star reduced, we need surjectivity because this conjecture is a theorem basically, or holds when the Baum-Cohn conjecture is surjective, then the values of L²-Betti numbers in degree n would be rational. And we saw that in principle they can be any positive number, but once we have surjectivity of the Baum-Cohn assembly map, then we would get finer range for our L²-Betti number in degree n of group. And of course, if G is torsion free, then this is integer because we don't have any finite subgroup here. So we would, besides the trivial one, and that's why we would end up with just integer here. Right. So far we could kind of reduce or make the values of L²-Betti numbers a bit finer. So we can still get finer results by basically appealing to coarse Baum-Cohn conjecture. So coarse Baum-Cohn conjecture is similar to the Baum-Cohn conjecture. There is an assembly map. There is a right-hand side which is operator algebraic or analytic, and there is a left-hand side which is more topological or geometrical. And then the conjecture is that this assembly map is an isomorphism. So instead of the reduced group C-star algebra here, we have the row algebra that can be associated to any discrete metric space with bounded geometry. So now what can we get out of this Coarse-Bound-Kohn conjecture with respect to Kazhdan projection is the following. Well, we would get an identity or equality between the values of L²-Betti numbers in degree n and Betti numbers in degree n. So just recall, Betti numbers are just defined as the dimension, the standard dimension of cohomology of G with respect to coefficient with respect to C as coefficients, complex numbers, and such a dimension lives inside natural numbers. While, as we saw, the L²-Betti numbers are just defined as the von Neumann dimension of this module that we saw. And as such, they lie in such an interval, basically. So there is quite a difference between what one can take as or obtain as L²-Betti number or Betti numbers. So the result or the conclusion of this theorem is that one has an identity between these two invariants for some, let's say, subgroups. And we will see what are the conditions to get this equality. So we assume that G is an exact residually finite group of type Fn plus 1. Well, type Fn plus 1 is required because it comes anyway with the definition of higher Kazhdan projection. And exactness is just for some technical reason. And residually finite assumption is basically what one usually needs in the context of Coarse-Bound-Kohn conjecture. So as an example of a group with these properties, one can think of free groups on N generators, on K generators, let's say it like this. So any free group would be an example of an exact residually finite group of type. Basically, free group is of type F2 even. Right. So residually finite means that there is a sequence of finite index normal subgroups. So that is what we have here. N, the filtration of finite index normal subgroups of G. We get a unitary representation associated with any of these normal subgroups. Take the direct sum of all this unitary representation in order to obtain one single unitary representation. And if we assume that our higher Kazhdan projection in degree n lives inside matrices over some matrices over the C-star algebra generated by this single unitary representation. And now, oops. So we assume Pn lives there or Pn exists. If the course if the Coarse-Bound-Kohn assembly map for this particular metric space that comes from the filtration is surjective, then we would get this identity or equality between these numbers for sufficiently large i's. So the way one proves it basically in just two words is one constructs two maps basically on the image of the row algebra. One would give us the L²-Betti number, the one for L²-Betti numbers, and the other one would give us for Betti numbers. And then one shows certain diagram constructed out of these two maps commute, and then commutativity would give us this equality on the range of these two maps being L²-Betti numbers and Betti numbers. So this is pretty nice. On the one hand, we get a stronger conclusion that Luke's approximation theorem. So Luke's approximation theorem says that L²-Betti numbers are just limit of standard Betti numbers. So let's say n. So if n is the normal subgroup here, so there is a limit involved, and what we have here is just that on the nose we get an identity. But on the other hand, Lux theorem doesn't need any assumption on like what basically on the existence of high Kazhdan projections or exactness. What Luke wants is basically just we start with a residually finite group of, I guess, type F2. That would be, I guess, enough in order to obtain this approximation results. But of course, we assume more, but in return, we get on the nose equality, while here there is a limit involved between. So exactness, and of course, what we assume about the existence of higher Kazhdan projections and surjectivity of course BAM-CON. So what he needs is just a group, a residually finite group of type F2, I guess. Maybe even finitely generated would be enough for him. Right. So this is one conclusion. And the other one is, of course, this gives in principle strategy to find counterexamples to the coarse BAM-CON conjecture. If we find different values between, if we find that L²-Betti numbers and Betti numbers are not equal, then this means that this would imply that the higher Kazhdan projection does not live in on the image of the coarse BAM-CON assembly map, and that would give rise. Of course, one needs to find the right group and then use this method. But in principle, that's a new strategy to find a counterexample. Right. So far we, like after we define these higher Kazhdan projections, we have seen some applications of it basically in different versions with respect to different versions of the BAM-CON conjecture. So maybe a question that might come to mind is, okay, so what are these actually these projections? Can we say something about the K-theory class of these projections? So as far as one can say, or one can say something with like by hand basically computing. So these are what one can obtain. So starting from infinite property T group, P0 is exact. So P0 would be Kazhdan projection. So that's just the numeration. So we have property T group. So there is a Kazhdan projection. We denoted by P0 just to fit in our higher degree setup. And if this is an infinite group, then we said that there is no invariant vectors, because invariant vectors are just the constant functions, and constant functions, when G is infinite, it would, a constant function that are L2 functions must be 0. So P0 is 0 once we are looking at a group with property T. Don't forget, P0 lives and it is non-zero inside C star max of G, but its image, or P, is in 0 inside C star reduced of G, basically. So that's what we obtain here. So next example is to take a free group on N generator. So we know that K0 of C star reduced of free group is Z generated by the class of 1. So this means that our projection is just a multiple of this, a multiple of 1. So what can we say more? Well, we can look at the first L²-Betti number of free group. So for degree N, or for free group on N generators, the first L²-Betti number is N minus 1. So that means that the P1, the K-theory class of P1 should be n minus 1 times the class of 1. So basically that describes the coefficient in front of K-theory, in front of 1. So what if we have some torsion? So just let's go a little bit further and consider a virtually free group, for example, PSL2Z. So PSL2Z contain F2 as a subgroup of index 6. And this means that our first L²-Betti number is 1,6. That's just the formula. And in particular, it means that the K-theory class cannot be inside Z. So it's not a multiple of the identity. Because the trace pairing this is just, and this is now 1,6. So this cannot be then a multiple of the identity. In the case of SL2Z or any virtually free group. So virtually free group means a group that contains free group that contains a free group as finite index subgroup, right? So what can we say then about P1 in this class? Can we basically, so we know that this is not a multiple of the identity, but can we identify this K-theory class from this basically numerical information that we have? Yes, we can. So let G be a finitely generated virtually free group. Let X be a tree on which G acts properly and co-compactly. Then we can describe the K-theory class of P1 as just a sum of projections associated with the vertices of the fundamental domain of this tree, or this of the action, minus the projections associated with the edges of this of the fundamental domain. So first, one thing, why do I just write P1? Because for virtually free group, there is only P1 that is non-zero. For the rest, everything else vanishes, since virtually free group basically is essentially free group. So virtually free group is just free group. And here, so cohomology in degree 2 vanishes here, while here cohomology in degree 2 is reduced, and that would basically provide us with the fact that P1 exists. And for the rest, cohomology vanishes, so there is no cohomology, hence there is no projection. So that's why we only have P1. Basically, we only need to be worried about P1, or we are interested only in describing just P1. And as such, it would be described like this. So maybe just one sentence about where does the motivation, so how do we prove it? Basically, the proof is by finding that the, very geometrically, basically, there is combinatorial Euler class defined by Hofmeier and Emerson. And they show that this combinatorial Euler characteristic is mapped, is under the Baum-Cohn assembly map to something that is described by finite, basically by averaging projection. So it's just a sum of, it's an alternating sum of some averaging projection. And before basically this theorem, our kind of conjecture or guess was that higher Kazhdan projections should live in the finite part of K-theory, namely the part that is generated by just the part that is generated by the finite subgroups of the group. So in other words, P1 or Pn should be just a sum of averaging projection associated with finite subgroups of our group. And then when we saw this, what we try to do is to show that basically this is exactly what we have. So, so to basically identify this term as our higher Kazhdan projection, and then we could basically say further that Euler characteristic is a pre-image under the Baum-Cohn assembly map for higher Kazhdan projection, of course, when they exist. So basically, this was what guided us to prove that in this case, one can describe the K-theory class of Kazhdan projection so easily, basically by the easiest construction that one can think of, namely averaging projection. So let's look back to the example of PSL2Z. So PSL2Z is one way to describe it is just a free product of Z mod 2 with Z mod 3. So in this case, the fundamental domain of the Boster tree that we have associated with PSL2Z is just an edge, basically. So this is Z mod 2, this is Z mod 3, and the edge that is labeled by the identity subgroup. So by our formula, our projection P1 is just basically identity minus the averaging projection associated to Z mod 2 being this vertex, and the averaging projection associated with Z mod 3 being the averaging projection associated to this subgroup. And here we would get identity. So identity minus these two would then be would define the K-theory class of P1.
K0 group what is this K0 group?
So the K-theory of the K0 group is Z to the 4. Z to the 4. But you mean what for C-star algebra it is?
No, but a specific thing.
Yeah.
Yes.
Yeah. It's Z to the 4, yes. So it's always, so for free product or for amalgamated free product, basically, so if this is our group, let's say, then the K-theory would be the sum of Z to the sum of these two numbers minus K minus 1. Yeah.
No, the other part. In K-theory,
oh, yeah, sorry. Yeah, that was right. Yes. M plus N minus K minus 1. And thanks. Yeah, sorry, right. So if G is Z mod N over Z mod K, K0 of is just Z to M plus N minus K minus 1. Actually, there's, yeah, that's just this, right? Yeah. And hence this is, yeah.
So this, volts, this,
Yes. So now, in the last part, I would like to give a different application to what we have seen so far, and that is going to be about trace pairing with respect to different traces than the canonical trace that I mentioned at the beginning. So what are these traces? So right, so we start with the discrete group and we fix an element, then tau g, so a delocalized trace associated, the delocalized trace associated with this element g is the following function. So it's a function defined, or a tracial function, functional defined in the L1 of g, such that when we are given a function on L1 of g, or CG, or a group ring, we look basically, or we sum up the coefficient of those elements in the group that are in the conjugacy class of this given little element. So before, we had just the identity, and we just look at the coefficient in front of the identity, and that was the value of this, the canonical trace. And now we are looking at the conjugacy class and of this element, and pick exactly those coefficients appearing there, and that is defining us a functional, and this is what we call, what it is called, delocalized trace. Pushnik has a very nice result for hyperbolic groups, saying that if right. So what is this result? So it says that there is a Schwarz algebra, or there is a smooth subalgebra inside C star reduce of G, such that it has the same K0 as the reduced C star algebra induced by inclusion. And interestingly, these delocalized traces that we defined here extend continuously to S. So we get a trace on this Schwarz algebra. And now if we extend this, this functional to the level of K-theory, then we would get a function defined on functional defined on the K0 of C star reduced of G, that we can do outpairing basically with the K-theory element. So it is defined for hyperbolic groups, and it constructs a Schwarz algebra inside C star reduced with these two valuable properties, basically, that allows us to define this delocalized traces not only on L1, but also on a larger subalgebra. So as such, this functional, we cannot extend this functional on the level of C star reduced. That would be our aim to do, but we cannot do it. But Pushnik's smooth subalgebra constructs something that is defined on this smooth subalgebra, and if we extend it to the K-theory level, we would get a trace basically defined on K0 of C star reduced of G. So that is what Pushnik's construction gives. Having this, we define basically an analog of L²-Betti numbers, namely delocalized L²-Betti numbers. So what would be our assumption? Basically, we start with the hyperbolic group, and we required our group to be type Fn plus 1, so that we can talk about this projection basically. And we assume that Pn lives inside our K0 group. So then the nth degree delocalized L²-Betti number would be just a trace pairing between these delocalized traces associated with G and the K-theory class of Pn. So what we had before was that L²-Betti number of G in degree n was just a pairing, the trace pairing between the canonical trace and degree n higher Kazhdan projection And what we can do now here is the delocalized version of this. Right. So obviously, we are in more restricted circumstances than what we had here for L²-Betti numbers, because here we basically, this is defined for any discrete group. But here we, and of course, we want group to be type Fn+1 in order to fit it in this setup. But here, we require that G to be a hyperbolic group. And this is because we only have push-nick result, basically, to extend these delocalized traces to the level of smooth subalgebra. If we would have more Schwarz algebra or smooth subalgebra for associated with for other groups, then we could, to which we could extend these delocalized traces, and they had same K theory. Basically, that will be fine, but basically the extension to the Schwarz algebra, that would be the main key. And if we would have more groups with this property or with this Schwarz algebra, then of course we could extend our definition here to a larger class of groups and not just hyperbolic groups. But as for now, this is what we have, and that is what we define as delocalized L²-Betti number. I should mention that John Lott introduced delocalized L²-Betti numbers in 1999 for smooth manifolds, and he defined it analytically as a limit of these delocalized traces of e to the power minus delta. So his definition for smooth for smooth manifold was this, and he defined basically whenever this limit exists, then we call that a delocalized L²-Betti number. So what we do is basically we define that for groups, and we right away say, okay, if we assume that this limit exists, and then this is, we can also write our Kazhdan projection as such limit, and this would be basically what we define directly as the delocalized L²-Betti number. And that's, yeah. So when Lott defines basically delocalized L²-Betti numbers for manifolds, so he does not have basically any non-vanishing results, or he cannot do calculations. Basically, he just obtains two vanishing results, but obtaining from this definition, basically, or being able to compute this limit is pretty hard task. So as a result, basically, there was no explicit non-vanishing computation for this delocalized L²-Betti numbers. So what we can then obtain using our higher Kazhdan projection is to obtain the first non-vanishing result for an infinite group. Of course, if the group is finite, then this is basically triviality to get non-vanishing result, but that's not the point. One wants to have it for infinite groups. And now, thanks to the fact that we could write or describe this P1 class explicitly, now the trace pairing between trace pairing for various G would basically allows us to describe completely the values of this delocalized L²-Betti numbers. So if we look at S, basically S here, so what appears as a coefficient in front of S is just -1/2. So there we get this. If you look at the identity, we would basically recover the first L²-Betti number. So 1 minus 1/2 minus 1/3, that's what we have here. And if G is infinite order element, then we would get 0. So basically, this describes completely the only non-vanishing, basically, delocalized L²-Betti numbers. In other degrees, in other degrees, because Pn vanishes for virtually for elements like for PSL to Z, or in particular for any virtually free group, since we have only P1, so that's the only non-vanishing one. For the rest, everything vanishes. So that's all what we can say about the delocalized L²-Betti number for the class of virtually free groups, or in particular PSL to Z. Let us see some sample vanishing results. Well, if G is a hyperbolic group, and we have Pn inside matrices over C star reduced, so if Pn exists, then if the nth L²-Betti number vanishes, then the delocalized one vanishes as well. Why? If the delocalized L²-Betti number vanishes, so this we define this as as the dimension, the von Neumann dimension of the cohomology, reduced cohomology. Reduced cohomology defines our higher Kazhdan projection. So if L²-Betti number vanishes, so this means that the projection vanishes, and as well the pairing with respect to any delocalized trace would vanish. So then one would get 0 as a result. So from the knowledge about L²-Betti number, or from the knowledge about vanishing of L²-Betti numbers, we get knowledge about vanishing of delocalized ones. And if we have a hyperbolic property T group, and we assume that Pn lives here, then the first L²-Betti number would vanish for all G. Why that? Because there is one characterization of property T that says the first cohomology vanishes with respect to any unitary representation. And when all unitary representation vanish, so this would imply that then the reduced one vanish, and that in particular higher Kazhdan projection vanish, and then the first L²-Betti number would also vanish. So this characterization about vanishing of cohomology associated with property T groups is just about the first degree. And that's why we can only obtain results about the first degree delocalized L²-Betti numbers. So yeah, so that so that's it. Yeah, please.
And from the audience?
Yes, when you say all the time, assume Pn is in this matrix algebra, by this do you mean assume that Pn exists?
Yes. So
okay.
that's a good question. Yeah. So this obviously Pn. So it's not that for any group Pn exists. So there is conditions guaranteeing that Pn exists, and that is the following. So that's a good question. Yeah. It was in this missing slide. So good at. So Pn in, so we define Pn inside some, let's say, matrices over this. So this projection exists if there's a spectral gap. So if let's say lambda in this case, because we are working with reduced group C star algebra, we can work with any unitary representation in principle, or any family of unitary representation to define higher Kazhdan projections. But here we have C star reduced, so that means like we are working with the left leg representation. So if this one has spectral gap, only then Pn lives in some matrices. And we can guarantee this existence by basically by saying that, so Pn, so there's a result by Bader-Novak saying that in our language, basically Pn lives inside matrices if cohomology in degree n and n+1 is reduced. And that is basically the condition that in practice we are working with, because finding spectral gap, maybe it's not so convenient, but checking whether cohomology is reduced, it's still not convenient, but it is something that one can work with and one can compute. So if this is the case, then Pn exists, and then we can basically get all these applications as we saw.
Thanks.
Yeah.
Any other quick questions before we move on to our next speaker? If not, let's thank Sanaz again. And maybe we take about a 5-minute break or so that we can reset up for Sven.